All right, so in this lesson, we're going to look at the inclined plane. We're going to do a little bit of math, just talk a little bit about its purpose. So the first thing, what's the purpose of an inclined plane? Well, it changes the force that's required to lift something. So instead of lifting something vertically, actually it's changing direction too, because we're applying force up the ramp instead of a vertical lift. But the biggest purpose is it reduces the amount of force or the amount of effort needed to lift something to a new height. So without the ramp, we would need to look at what's the weight of the ATV, or what's the mass of the ATV times the gravitational constant, and that would be the force needed to lift it. But when we're pushing up a ramp, we're going to find that we use less force in order to move it. Okay, so the ramp is really supporting some of that gravitational force. So it's just a flat surface set at an angle. Easy description. We don't have to describe too much of it. That's pretty elementary. And the other important thing that we're going to find when we talk about a ramp is the roughness of the ramp is going to have a major impact on efficiency. So the more rough the ramp is, the less efficient. Although sometimes we need that roughness or our wheels won't grip. So it's one of those kind of catch-22s. All right, so why does an inclined plane reduce effort force? Now I'm going to try to explain this without getting into the nitty-gritty physics. If you were part of a full year physics course, I would have discussed and we would have gone through how that we can break forces into what we call components. So we can look at force, when force is on an angle, we can use trigonometry to figure out how much force is down and how much force is horizontal. But we're not in that course and we don't have to do trigonometry. But I'm going to kind of show you how it works, and we're just going to kind of give you a description. So this box, let's say we want to lift it. If we want to lift it a distance, a relatively short distance, we're going to have to use more force because we know that force times distance in has to equal force times distance out. And the output in this case is what we would lift with if we didn't have a ramp. So the output is without ramp. And we've talked about that when we talked about energy. It's the same as the energy required to lift an object. So it's going to be mass times gravity times how high we lift it. Or we can think of it as force caused by gravity. So mass times gravity times the distance that it's lifted. Okay, so work and energy work the same, calculate the same way for us. All right, so what about if I'm pushing it up the ramp? Well, when you push an object up the ramp, I want you to look at this picture for a second. The weight or gravity always pulls straight down on an object. Now, some of the gravity pulls this cart down the ramp, but not all of it, because some of it is holding it on the ramp. And if you were part of the big physics course, spends a whole year instead of a couple weeks, we would draw a triangle like this. And we would say, well, this is the force of gravity pulling straight down, but some of that gravity holds the cart on the ramp. Some of the gravity, and that's this part, pulls down the ramp. Now we haven't done trig, and I don't expect you to remember this. But you might remember from high school, you might not. It might have been a while since you did high school. This force, this side of a triangle is the hypotenuse. It's always the longest side. So if the force of gravity is like the hypotenuse of a triangle, it's always bigger. That's the force that we would be counteracting here. It's always bigger than the part that pulls down the ramp. So the reason we have less force is some of the gravity holds the box on the ramp, while the rest of gravity is what we have to push against to push it up. And it's only a portion of the gravity. So that's why an inclined plane reduces the effort. Okay, it helps support some of the gravitational force. Now, the steeper the ramp, the more of that force of gravity is going to be pulling it down the ramp. So the harder we're going to have to push up, or the more effort we'll have to put in. But the more shallow the ramp, we'll have to push a longer distance, but we won't have to push as hard. So hopefully that kind of explains why. I'm not going to quiz you on that. I won't make you deal with the triangles. You don't have to worry about it. but I want to kind of show you why it is. And hey, take something like a binder, or a ruler, stick something on it and look at how easily it slides down. The easier something slides down, that means the more work you're going to have to do to push against gravity in order to push it up to the top. So that kind of gives us a good visual for ramps. And I know you get, most of you have probably had some experience using ramps. All right. So an inclined plane can reduce the force needed to lift a load in two ways. One of the ways is by increasing the length of the ramp, and the other one is decreasing the height of the ramp. Oops. So in this particular ramp, you'll see up the ramp, we push a longer distance. The effort distance is big, while the effort force is small. If one is large, the other one will be small. Compared to the load force and the load distance, you'll see the load distance is shorter. It's always going to be shorter, but the force needed to lift it is always higher. Okay, so if we want to reduce the amount of force, we either have to make the ramp longer or we have to make it not quite so tall. Usually, we can't change the height. There's a reason why we're using a ramp. We want to get to a height. So usually we can't change the height, but we can increase the length of the ramp. Now, there is a situation I can think of where the height of the ramp comes into play. Anybody ever see U-Haul's ad? And they advertise the easiest to, their trucks are the easiest to load. And the reason they advertise that is because the back of their truck is closer to the ground. So U-Haul trucks, they decrease the height of the ramp that you need, which means you need less work. So that's why if you rent a U-Haul, it's going to be a U-Haul truck for moving. They advertise that it's the easiest truck to load. It requires the least amount of work because the height of their ramps would need to be shorter. You don't have to lift as high. Next time you drive by Lockhart's gas station and the U-Haul trucks, take a look and see if that's still advertised on the side. But usually it's advertised on the side that they have the lowest loading deck, which means the least amount of work. And that's just simply using these formulas. So I'm going to take a second. I want you to do a think and apply. You know how much I love think and apply questions. So some friction is needed for the wheels to grip the ramp and climb. That's important. If you don't have any grip, it's just going to slide. But how will friction impact the force you apply to climb the ramp? And how will it impact the efficiency of the ramp as a machine? Well, if there's friction, I have to fight friction. I have to put more force in to move something that has friction, because friction always works against you. So if there's friction, it might help my wheels grip, but it means we're going to have to put in more force. How does that affect efficiency? Well, if I have to put in more force, we've learned that efficiency, it would be ideally what I'd have to put in and then what I actually have to put in. We can compare, we could think of it that way too. So the efficiency, if I have to put in extra work and I don't get as much mechanical advantage, I don't have as much efficiency. So if there's friction, we'll always be less efficient and more force. So the force will be higher, but the efficiency will be less. But it's a trade-off. Sometimes that friction is needed. Okay. One of the reasons we use wheels, and we'll do wheels with next week's lesson, wheels reduce friction because there's a smaller surface in contact. They help us with that. So this friction is maybe better to visualize if you were sliding something like a box or something up a ramp. All right, so let's do a little bit of simple machine math with an inclined plane. If you have a 268 kg ATV, apparently that's a standard weight, and it's loaded onto a truck bed that's 0.8 meters high from the ground using ramps that are 1.4 meters long. I want to know how much work is required to get the ATV on the truck. So I'm going to make you think back. We've kind of reviewed work in your last lesson. Work equals force times distance. Now it's force and distance have to be in the same direction. So to get the ATV on the truck, I have to lift it up 0.8 meters And I have to lift up with how much force? Well, the force that I have to lift up with is the force of gravity. How do I figure that out? I did that earlier. Let's see if we remember. Force of gravity is the force I'm working against. So it's 268 times 9.81 gives us 268 times 9.81. Let me turn to where I've actually calculated this rather than putting it in my calculator again. Gives me 2,629 newtons. It's quite a bit of force. How much work do I need to do? Well, let's figure that out. Gravity pulls straight down, so we need to look at the vertical height that we're moving, not the ramp length. So let's figure it out. I need to use 2,629 newtons of force to lift up this ATV times 0.8 meters, the distance up I need to move it. The amount of work that you would do is 2,103 joules. That's how much work would be required. 2 kilojoules. You could do 2 kilojoules of work. It's really not, in terms of work, the amount of work is not the issue. The issue is how much force you'd have to apply. Most of you, I should be careful saying how much you guys can lift. I might be surprised. How much force? So most of you, I'm guessing, couldn't, it's kind of awkward. On your own, you couldn't lift that ATV up vertically to get it onto the truck. You'd need to use the ramps. Well, how much force is needed? How much less force is needed if we want to push it up the ramp? So this question says how much force is needed to push it up the ramps if it's ideal. So we're going to ignore friction. Well, work in equals work out. Okay, so that means force times distance has to be equal to, this is the ramp, has to be equal to the force times distance of lifting, which is what we calculated here. So 2,103 joules. And I didn't leave much space to work. Let's see where I can squeeze this in. I think I can do it here. Force times the ramps are 1.4 meters equals 2,103 joules. Divide by 1.4, divide by 1.4, and we get the force is equal to 1,502 newtons of force. Now, to put that back into kilograms, if you want to visualize how many kgs of force would that be, you could also convert it to pounds if you wanted. But if we divide that by gravity, that would be like 153 kgs of force. So quite a bit of force, but not nearly as much. Our force, you'll notice the force, it's not quite half, but it's getting close. All right. And I just took those as standard ramp heights. So even in terms of the engine needs to apply less force if you're climbing up your ramp. If we factor in friction, what will happen to the force needed? The force will increase. Friction always increases the force we have to put in. I might try switching my pen color on the next slide because all that red ink kind of blends in together. All right, let's try this one. Let's go with the blue ink. What's the ideal mechanical advantage of the ramp? And I seem to be missing some text. That's okay. IMA is equal to the ideal mechanical advantage uses distance. So distance, now which one goes on top, effort or load? Effort. And then you have loads. And then the actual mechanical advantage uses force because it's changed by friction, and it's the force of the load, because it's usually larger, divided by the force of the effort. All right, so what's the ideal mechanical advantage of the ramp in the picture? We'll define the ideal mechanical advantage. All we need to do is, what's the distance that the effort moves? It moves 15 meters. What is the distance that the load actually moves, the vertical distance that the load we want to move the load, and that's 4 meters. So the ideal mechanical advantage is 3.75. You'll notice meters and meters make the units match before you find it. What's the actual mechanical advantage though? Now here's where we have a trick. And I know we've done all of our stuff using force by finding how many newtons there are. But when it's a ratio, we can actually do the ratio using pounds to find the mechanical advantage, or kilograms, as long as both of them are in pounds or both of them are in kilograms. So you can talk about how many pounds of force and how many kgs of force. It's not the true physics definition, but we could prove from math that it actually works. I'm just going to say it works. I'll let you work with it. So if you're told something in newtons, you'd have to think about gravity, kind of think about the last section. But if it's just something that uses, wants to know mechanical advantage and it's force divided by force, you could do pounds divided by pounds, or you can do kgs divided by kgs. We're going to find we can do that quite often. So we'll often kind of compare force using kgs. So the actual mechanical advantage is going to be the force of the load. So our load is our 50 pounds. Now, if I did 50 times 9.81 on the top, and then on the bottom, I put my effort, which is 20 times 9.81, finding it as force, you'd find the gravity parts in 9.81, they would cancel out. So it goes back to 50 divided by 20. Now, if that math is a little confusing, don't worry about it. Just so you can follow along. For force, if you're comparing two forces, you can compare pounds and pounds. All right, now that we have this, what do we get for mechanical advantage? Hopefully you've calculated 2.5 as well. We get a lot less work out than what the ramp says we should. There must be some friction involved in this ramp. So what's the efficiency? Efficiency is the actual divided by the ideal times 100. Actual is 2.5 times 3.7 divided by, 3.75 times 100 leaves me with 67% efficient. And it's less than 100, so we've done our math correct. If we had it flipped, we would get a number over 100, and that wouldn't work very well. So that gives us just a couple examples of inclined plane math. You won't have a lot of it, but I want you just to kind of think about the principles. And that's all we have for inclined planes.